Welcome to the video lecture series Digital Filter Design and its Application. The subject code is the ACE 103. My name is Dr. Anilesh Dey, Associate Professor, Department of Electronics and Communication Engineering, Narula Institute of Technology. Sharing this course, one of the renowned Professor Dr. Sholil Kumar Shandal. Dr. Sholil Kumar Shandal, retired professor and head, Department of Electronics and Telecommunication Engineering, Jadavpur University. Presently, Professor Sholil Kumar Shandal working as a professor, Department of Electronics and Communication Engineering, Narula Institute of Technology. This course is designed for the MTech in Electronics and Communication Engineering students. This is lecture 7. In the previous lecture, I had already discussed the characteristics of the Chebyshev filter, where I explained there is in the type 1 Chebyshev filter, there is the equiripple in the pass band and there is a monotonic in the stop band. In the type 2 Chebyshev filter, there is the monotonic in the pass band and equiripple in the stop band. I also discussed the characteristics of the Chebyshev filter and already derive the order of the filter n, which is equals to cos h inverse root over of 10 to the power 0.1 alpha s minus 1 divided by 10 to the power 0.1 alpha p minus 1 whole divided by cos h inverse omega s by omega p. In the last lecture, I already discussed the pole location of the Chebyshev filter. Today, start with the steps to design an analog Chebyshev low-pass filter. Step number 1, from the given specification, find the order of the filter n. Round off it to the next higher integer, it is a step 2. Step 3, using the formulas to find the value of a and b, which are the major and minor axes of the ellipse respectively. A equals to omega p within bracket mu to the power 1 by n minus mu to the power minus 1 by n divided by 2, and b equals to omega p mu to the power 1 by n plus mu to the power minus 1 by n divided by 2, where mu equals to epsilon to the power minus 1 plus root over of 1 plus epsilon to the power minus 2, and epsilon equals to root over of 10 to the power 0.1 alpha p minus 1, where omega p equals to passband frequency and alpha p equals to maximum allowable attenuation in the passband. For normalized Chebyshev filter, alpha p equals to 1 radian per second. Calculate the poles of the Chebyshev filter which lie on the ellipse by using the formula. This is a step 4. The formula is Sk equals to A cos phi k plus J B sin phi k, where k equals to 1 to n, and where phi k equals to pi by 2 plus 2k minus 1 divided by 2n into pi, where equals to k equals to 1 to n. Find the denominator polynomial of the transfer function using the above poles. This is the step number 5. In step number 6, the numerator of the transfer function depend on the value of the n. For n is odd, substitute s equals to 0, denominator polynomial, find the value. The value is to the numerator of the transfer function. For the n odd, magnitude response mod of j omega starts at 1, which I described in my previous lectures. For n equals to even, substitute s equals to 0, the denominator polynomial, and divided the result by root over 1 plus epsilon square. This value is equal to the numerator. These are the design steps of the analog low-pass Chebyshev filter. Now I explain each and every step with the help of a problem and design the analog Chebyshev filter in the next slide. The problem statement is that from the given specification, alpha p equals to 3 dB, alpha is equals to 16 dB, fp equals to 1 kilohertz, fs equals to 2 kilohertz. Determine the order of the filter using Chebyshev approximation of hs. Solution. From the given data, fp is given in the hertz, so I converted that thing in the radian per second. So omega p equals to 2 pi into 1000 hertz, that is 2000 pi radian per second, and fs is given the 2 kilohertz, that is a 2000 hertz. So convert it into the radian per second. So omega equals to 2 pi into 2000 hertz, that is a 4000 pi radian per second, and alpha is equals to 3 dB, and alpha p equals to 3 dB and alpha equals to 16 dB, which is given. Now step number 1, to find the order of the filter, we know the formula n greater than equals to cos h inverse root over of 10 to the power 0.1 alpha is minus 1 divided by 10 to the power 0.1 alpha p minus 1 whole divided by cos h inverse omega s by omega k. Now put the value alpha p, alpha s and omega p, omega s in this particular equation, and we can find the value of the order of the filter, that is the 1.91. Now step 2, rounding the n to the higher value of the integer, that is the n equals to 2, because we can find that n equals to 1.91, so that's why n equals to 2. For n even, the oscillatory curve starts from 1 by root over of 1 plus epsilon square. This value, step 3, the value of the minor axis and major axis can be found as below. Epsilon equals to root over of 10 to the power 0.1 alpha p minus 1, to put the value of alpha p over here, and epsilon equals to 1, and mu equals to epsilon to the power 1 plus root over of 1 plus epsilon to the power minus 2, mu equals to epsilon to the power minus 1 plus root over of 1 plus epsilon to the power minus 2, and value of the 2.414, and a equals to omega p mu to the power 1 by n minus mu to the power minus 1 by n divided by 2. So what is the value of the mu? We can get it from here, and omega p equals to 200 pi, and n equals to 2, put the value and get the a equals to 910 pi. Similarly, we can get the value of the b, and b equals to 2197 pi. The poles are given by the equation sk equals to a cos phi k plus j b sin phi k, k equals to 1, 2, and phi k equals to pi by 2 plus 2k minus 1 divided by 2n into pi. Now for the k equals to 1, phi 1 equals to, put the value of the k equals to 1 and n equals to 2. So phi 1 equals to pi by 2, this pi by 2, and this is the pi by 4, because 2 into 1 is 2 minus 1 is 1. 2 into 2, that is the 4, so that is pi by 4, that is 135 degree, and phi 2 equals to 225 degree. Now S1 equals to, put the value of the a and phi 1 and get the result of the S1. Similarly, we can go for the result of the S2. Now denominator of h is equals to s plus 643.465, which is getting from the last equation, square plus 1 554 pi square. There we can get the denominator, and this is the we can get the numerator of the h's, that is the 1414.38 whole square into pi square. Now transfer function, we can put the numerator and we can put the denominator, we can get the transfer function of the h's. So this is the designing process of the analog low-pass Chebyshev filter. Now we describe the Chebyshev 1 low-pass filter using MATLAB code. Now this is the declaration portion where the alpha p, alpha is omega p, and omega p I declared. Now to find the cutoff frequency n into omega n, that is a Cheb 1 order omega p pi comma omega s pi alpha p and alpha s. So from here we can get the cutoff frequency. Now I can write the sixth step b comma a equals to, this is the function of the Chebyshev 1 filter Cheby1, and n alpha p omega n, and we can give the range of the omega n, and h p phi equals to frequency z ba omega. Now we can get the find the magnitude and as well as the angle, and subplot for the magnitude and for the phase. So this is my output of the Chebyshev 1 low-pass filter. Now we can go for the Chebyshev 2. All at the similar, only you can use the formula syntax Cheby 2 over here, and here also the Cheby 2 instead of the Cheby 1 in the last program where I find out the Chebyshev 1 low-pass filter. And similarly we can go for the magnitude and angle plot, and this is the output of the Chebyshev 2 analog low-pass filter. So this is the reference These are our contact details. Feel free to write us in this particular email IDs. This is the email ID of Sannal sir. This is the email ID of me. And so this is the end of lecture 7 and meet you in lecture 8. And if you like, then please subscribe our YouTube channel. Thank you.